Standard sustainable design focuses on minimizing damage. We build static concrete boxes, then attempt to offset the impact by reducing emissions or adding a minimal green roof. Reversing urban degradation requires moving toward a model of regenerative mobility, where the infrastructure itself performs the work of ecological restoration. This involves a transition from inert concrete structures to living metabolic architectural systems that actively process and filter the resources in their immediate environment. The most effective locations for these systems are high-traffic urban transit nodes. These intersections currently generate the highest concentrations of localized pollution and energy demand. Instead of viewing these transit bottlenecks as unavoidable environmental burdens, we can treat them as the primary sites for localized ecological recovery. This map identifies Bengaluru's Silk Board Junction, a site defined by intense urban density and its proximity to Madiwala Lake. This junction is a critical transit node where current infrastructure has reached a complete breaking point under the weight of daily traffic volume. The environmental cost is measurable. The zone registers critically high concentrations of PM2.5 and PM10 particulate matter, trapped by the constant flow of combustion engines. The surrounding impermeable concrete creates urban canyons. These structures trap vehicle emissions and amplify heat, driving a severe urban heat island effect. Without vegetation or permeable surfaces, seasonal rainfall cannot reach the soil. Instead, it mixes with road contaminants to create toxic surface runoff that frequently floods the junction. Furthermore, maintaining a transit hub of this scale requires a constant high-volume energy draw from the regional power grid. This framework compares the site's current stressors, the environmental costs it takes, against the regenerative outputs a new hub must provide to the city. Because the existing degradation is so severe, an intervention at Silk Board Junction offers the highest potential for impact. It can function as a tangible lung for one of the city's most stressed zones. The proposed Lung of the City project utilizes a 4-layered metabolic architecture, as shown in this exploded axonometric diagram. At the foundation, Layer 4 is engineered to manage toxic surface runoff. Permeable paving and integrated bioswales use biological filters to strip heavy metals and toxic oils from the water as it leaves the road surface. This zero-discharge system captures water on site, preventing runoff from overwhelming the municipal stormwater drains. Once cleaned, the filtered rainwater is directed underground to actively recharge local aquifers. This closed-loop system provides 100% of the irrigation needed to sustain the hub's vertical gardens. Through biofiltration, the transit hub functions as a localized water-generating asset that mitigates the risk of flooding. Standard transit infrastructure relies on massive, static concrete pores. These structures carry a significant debt of embodied carbon before the first commuter ever arrives. The lung utilizes a different structural approach, detailed here in Layer 3. The framework is composed of a high-performance ultra-tech concrete mix. By incorporating supplementary cementitious materials like fly ash, the structure strictly minimizes its carbon footprint. The design uses a precast modular grid. These dry bolted joints allow for rapid, waste-free assembly during the construction phase. This assembly method enables life cycle circularity, a design principle centered on the longevity of materials. At the end of the hub's operational life, the concrete skeleton can be unbolted and disassembled. This allows the structural components to be reused in new projects rather than being demolished. Reusing the physical building blocks of the city is a necessary step toward eliminating construction waste. Layer 2 consists of the biofacade, the active component that gives the project its name. This facade uses microalgae photobioreactors. Through a closed-loop sunlight-to-biomass conversion, the system sequesters carbon significantly faster than a traditional tree canopy. Integrated IoT sensors monitor local PM2.5 levels in real time, allowing the system to dynamically adjust the algae's pumping rate to maximize air purification. The resulting microalgae biomass is harvested periodically, serving as a localized organic fertilizer for the city's green spaces. Pairing this biological skin with the high thermal mass of the concrete frame provides significant acoustic and thermal insulation. This combination absorbs high decibel traffic noise and reduces ambient surface temperatures by up to 4 degrees Celsius. Powering these active biological systems and the station lighting requires a reliable energy source that does not strain the municipal grid. Layer 1 addresses this through an integrated metabolism energy canopy. A roof-integrated solar photovoltaic skin generates decentralized power. This creates a net positive energy loop that sustains the hub's internal operations. By combining biological air filtration with renewable energy production, the hub functions as a self-sustaining metabolic organism. Deploying complex biofiltration across various urban topographies requires a flexible, non-static design. The modular concrete framework is a kit of parts, capable of reconfiguring to meet the needs of diverse urban sites. The lung of the city is designed as a scalable infrastructure model. These modules can be scaled down to fit the specific footprint of a standard neighborhood bus shelter. They can also scale up to accommodate the heavy structural requirements of major railway terminals like Majestic. This scalable grid also addresses the friction between pedestrians and vehicles found beneath existing metro stations. The framework supports elevated green walkways that connect metro lines to BRTS corridors. This design prioritizes pedestrian safety by separating foot traffic from the road level. Connecting isolated restorative interventions into a citywide network is essential for genuine urban regeneration. The projected impact of this project is significant. An estimated 40. The integrated microclimate reduces the urban heat island effect by up to 4 degrees. These metrics demonstrate that infrastructure can be engineered to contribute more to its environment than it takes. Realizing this goal requires looking past simple harm reduction as the primary objective of sustainable design. Restoring the urban environment requires design that prioritizes public health and site-specific ecological needs. By reimagining our most degraded urban intersections as sites for active biological recovery, we can build cities that finally breathe.